everyone, I am Assistant Professor Komal Shinde and this is your fourth lecture on a partial differentiation. In first three lectures we have seen the partial differentiation, means what is the definition of a partial differentiation, how we can find out the partial differentiation, then how to find the total differentiation. So in this lecture we are going to see how to find the exact differential equation. We know that if I am having a function f which is a function of x and y, then its total differentiation is given by df is equals to dabba f by dabba x dx plus dabba f by dabba y dy. If this differential equation is equal to 0, means we get a differential equation in this form: df is equals to dabba f by dabba x dx plus dabba f by dabba y dy, and this equation is said to be exact differential equation if there is certain conditions to be satisfied. That condition is that, means this equation is having partial derivatives terms, means dabba f by dabba x and dabba f by dabba y. We call it as m and this term as n. Here you can see m is equals to dabba f by dabba x and n is equals to dabba f by dabba y. This m and n are also again a function of x and y. So the exact differential form of this equation will become df is equals to m dx plus n dy, and if we further differentiate this equation with respect to x and y, you will get dabba square f upon dabba y dabba x is equals to dabba m by dabba y, and dabba square f upon dabba x dabba y is equals to dabba n by dabba x. If these two equations are same, means after further differentiating m and n with respect to y and x respectively, if this condition is satisfying, then we can say that above differential equation is actually an exact differential equation. And if it's so, then we can find the function. And if this condition, means this condition is not satisfying, dabba m by dabba y is not equals to dabba n by dabba x, in that case we can say that this df, means the total differential function, is not exact differential equation, and for that case we cannot find the f, means we cannot determine the f. So let us see with the example. Here I have considered one differential equation, total differential equation. df is equals to 5x square plus 3y dx plus 3x minus 5y square dy. If you compare this with the exact differential form, that is df is equals to m dx plus n dy, m will be 5x square plus 3y and n will be 3x minus 5y square. If we differentiate m with respect to y and n with respect to x partially, then you will see the differentiation of m with respect to y will be 3 and differentiation of n with respect to x partially will be 3. So this condition is satisfying actually. Dabba m by dabba y is equals to dabba n by dabba x. So we can say that the above total differential equation is actually the exact differential equation if this condition is satisfying. Consider one more example. Here df is equals to x dy plus 3y dx. If I compare this with this exact differential form, m is 3y and n is x. Okay. So dabba m by dabba y is 3 and dabba n by dabba x is equals to 1. Means this dabba m by dabba y is not equals to dabba n by dabba x. So in this case we can say that the differential df is not the exact differential, and in such a case we cannot find out the f. So in the above case we can determine the f, but in this case we cannot define the f. Now we will see this problem. Show that this df, that is total differential equation, y square plus y plus 2xy dx plus x square plus x 2xy dy is exact differential. So what is the condition for exact differential? Dabba m by dabba y should be equals to dabba n by dabba x. If this condition is satisfying, then we can say that the above differential is an exact differential equation, and in that case we can find out the f. So first we will compare this given equation with the exact differential equation form, that is df is equals to m dx plus n dy. So here m is, after comparing y square plus y plus 2xy, and n will be x square plus x plus 2xy. Now let us see whether this condition is satisfying or not. So we have to differentiate dA by m by dA by y, means we have to differentiate m with respect to y partially by keeping x constant. So that differentiation will be 2y plus 1 plus 2x, and if I differentiate this n with respect to x partially by keeping y constant, I will get 2x plus 1 plus 2y. If you observe these two terms are same, means this condition dA by m by dA by y is equals to dA by n by dA by x is satisfying. Then we can say that the above equation df is actually a exact differential equation. So this type of a problems comes in exam, means whether the given function is exact differential or not. So in this way you have to solve. If this condition is satisfying, then you can say yes, it is exact differential, and if this condition is not satisfying, in that case you can say that the above equation is not exact differential and we cannot determine the f. The next subtopic of this chapter is theorems of differentiation. So there are total 2 theorems of a differentiation. First we will see the first theorem and then second theorem. So far actually we have discussed this function f of x is a function of 2 variables x and y, means it depends upon x and y, means as x changes or a y changes, that function is changes. Okay, now we can express this x as a function of f and y as a function of f and x, and for this purpose what we are doing, we are replacing this f by z. So x can be imagined as a function of a y and z, means we have replaced that f with a z, that is x is a function of y and z. Therefore the total differentiation of this x will be dx is nothing but dA by x by dA by y at a constant z dy plus dA by x upon dA by z at constant y dz. So this is equation 1. Similarly, we can imagine y as a function of x and z. So total differentiation of y dy is equals to dA by y by dA by x at a constant z dx plus dA by y by dA by z at a constant x dz. I called it as equation 1 and this equation 2. Now you can substitute this dy in equation 1 over here. So substituting the value of a dy in equation 1, what we will get, just you have to substitute this dy over here. You will get dx is equals to dA by x by dA by y at a constant z, then substitute that dy. So in bracket dA by y by dA by x dx plus dA by y by dA by z dz plus that second term as it is dA by x by dA by z at a constant y dz. Now we will take the dx term together and dz term together. So dA by x dA by y at a constant z and dA by y by dA by x at a constant z dx, we have combined this term plus here dA by y by dA by z, then dA by x by dA by z, and third term dA by x by dA by y. So dA by x by dA by y, dA by y by dA by z, dA by x by dA by z dz. So we have rearranged this above equation and I have called that equation number 3. Means out of the 3 coordinates x, y, z, any two are actually independent coordinates. So let us consider, means we are going to choose x and z as a independent coordinates in the above equation. So the above equation must be true for any value of dx and dz. Why? Because there are 3 coordinates, you can see x, y, z in equation number 3, and any two are actually independent and one will be the dependent coordinate. So what we have done, we have chosen x and z as a independent coordinates. So for any values of this x and y, the above equation must be true. Suppose I have taken dz is equals to 0 and dx is not equals to 0. In that case, what I will get? means dz is not equals to 0 but dx is equals to 0, means this term will become 0, and what I will remain with dabba y by dabba x at a constant z, and dabba y by dabba x at a constant z is equals to actually 1, or I can write dabba x by dabba y at a constant z is equals to dabba y by dabba x at a constant z inverse, or 1 by dabba y by dabba x at a constant z, and this equation is actually nothing but theorem of differentiation. This is the first theorem of differentiation. Just we have taken dz is equals to 0 and dx is not equal to 0, and therefore the third expression becomes the first theorem after considering dz is equals to 0 and dx is not equals to 0. The relation given by this equation, that is theorem 1, is also known as the reciprocity relation, and which holds good provided both the partial derivatives should exist and neither equal to 0, then only these theorems will hold good, and it is also known as reciprocity relation. And one point should be noted that actually the relation, means the theorem 1, holds when the one variable is kept constant, means in this case we have taken z as a constant, you can see, means the one variable is constant over there in both side of the above equation, means here also z is constant and here is also z is constant, so you should note this point also. Now we will see the second theorem of differentiation. So alternately we can put dx is equals to 0 in the previous case when we want to prove the theorem 1. In that case we have taken dx is equals to not 0 and dz is equals to 0. So alternately we can take dx is equals to 0 and dz is not equal to 0. So in this relation, means in this equation you can see that this bracket term will equal to 0, and we can call it as a cyclic relation, means when we put this dx is equals to 0, this bracket term will be equal to 0, and this is called as actually, or we will obtain actually a cyclic relation. So dabba x by dabba y at a constant z, dabba y by dabba z at a constant x, and this term, third term, dabba x by dabba z at a constant y is equals to become, or it will become 0. Or you can write in this way also, this plus term you can take on a right side, it will become a minus, and if we rearrange these three terms, means dabba y by dabba z at a constant x, this is as it is, then dabba z by dabba x at a constant y, we just flip in order to take on the left side, and this term dabba x by dabba y at a constant z is equals to minus 1, and this equation actually the second theorem of partial differentiation, and this is the first theorem of partial differentiation. So the second theorem will hold good unless any of the derivative is vanishes, means once the any one of the derivative is vanishing, this expression will not hold good. I am talking about this expression, that expression will not hold good in that case. So in deriving this result, that is theorem 2, we have used the reciprocity relation to replace dabba x by dabba z at a constant y inverse by dabba z by dabba x at a constant y. So these two theorems are important in the partial differentiation.